Human-caused climate change is really the defining challenge of the 21st century. The changing climate puts lives, ecosystems, and economies at risk. We're already seeing impacts around the world, impacts that are increasingly severe, widespread, and in many cases irreversible. Today, we're fortunate to be joined by three leading experts who will provide a rich picture of the current landscape of understanding, as well as a vision of the steps we need to take to solve the challenge. The first presenter, I'm thrilled that we're joined by Professor Ramanathan. Dr. Ramanathan is the Edward A. Freeman Endowed Presidential Chair in Climate Sustainability at the University of California, San Diego, and the Scripps Institution of Oceanography. In 1975, Dr. Ramanathan discovered the greenhouse effect of chlorofluorocarbons and established the now accepted fact that non-CO2 gases are a major contributor to planet warming. This work also enabled the Montreal Protocol to become the first successful climate mitigation policy. Dr. Ramanathan's research projects track the huge span of his interests, ranging from clouds and climate to indoor air pollution. His pioneering work has been recognized with many honors, including election to the US National Academy of Sciences and the Royal Swedish Academy. He's been awarded the Tyler Prize and the Blue Planet Prize, and appointment to Pope Francis's Holy See delegation to the historic 2015 Climate Summit. Professor Ramanathan.
Thank you, Chris. Let me just see if I can share my screen. Can you see my full screen now?
That's perfect.
Okay. I'm really delighted and honored to be a part of this group. And this meeting comes at a very critical time. I know it's a long, 1 hour long presentation. So I'll just tell you, mine is just 15 minutes. If you forget everything I say, I would like you to remember this one thing, which is climate change is accelerating so rapidly, not only the warming, but also all the weather extremes, melting of glaciers, et cetera, et cetera. So we can't afford anymore to just rely on mitigation. Some of the so-called dangerous changes are already in the pipeline. So we need to broaden our approach to fighting the climate crisis. We should bring in adaptation and resilience building in the fore. And I'll tell you what those components are. So let me just give you a brief summary. So this is from the IPCC report, which was released last year, the Working Group 1. Basically, what they concluded is that the planet is warmer than any temperature experienced during the last 2,000 years. So this one shows the record. Some are proxy records, and some are really observed temperatures, starting from year 1 to 2020. So clearly, there is no doubt the warming is proceeding, unfortunately, exactly what many models predicted. So all of this was predicted, and we are seeing this unfolding. So we crossed about a degree warming about 2014, 2015. So you can ask, so what? Just a degree warming. And I want to first give you a brief, very brief introduction to the science of climate change. So why is the planet warming? We are putting many gaseous pollutants in the atmosphere. Carbon dioxide is the most potent one, just comes from fossil fuel burning. And the lifetime of these gases, particularly carbon dioxide, is so long, and that it covers the entire planet like a blanket within few years, 5 years maximum. So we have covered the planet with a blanket of these heat-trapping gases. So how much CO2 have we emitted? Look at the bottom value. That's 2.4 trillion tons. Okay, so that's how much we have dumped into the atmosphere. Imagine that. And about half of that, about 46%, is still in the air, the 1 trillion ton thick. Okay? It is that blanket of CO2 and other gases which are trapping the planet's heat and heating it. Just basic quantum mechanics and physics. So you can ask, so why should we care about the degree warming? And IPCC recorded numerous extremes: extreme heat, heavy rainfall, drought, fires, ocean warming, acidification of the ocean, and sea level rise. The first four we are experiencing already, and the next two is happening, but we will feel the severity of it in about 20, 30 years from now. And they just documented, I'm just going to tell you just two of these. Hot temperature extreme frequency increased by 180%. Heavy precipitation increased 30%, and numerous lives lost. And some of the countries suffering the worst is US, China, India, Philippines, and Indonesia. Unfortunately, just this early this week, from last week, India is experiencing one of the most severe heat waves, about 45 degrees. To my American friends, we are still in the Fahrenheit world. That's about 113, 114 degrees Fahrenheit. And look at the entire country, dark red. And so now come to what next, okay? We have already seen the degree warming. We are seeing heat waves. We are seeing fires. We are seeing floods. We are seeing droughts. So what next? This is a prediction we made with two of my colleagues, that we will cross the 1.5 degree warming in 2030. That's just 80 years from now. At that time, IPCC was still claiming that 1.5 would be crossed by 2040s. But in the most recent report released last year, they have come around to the view that we are going to cause 1.5 degree warming in about 80 years. They say early 2030s. So what does that mean? Imagine the degree warming linked with all these extremes. So when you go from 1 to 1.5, that's a 50% amplification of the warming in just 15 years, okay? So I wanted to tell you, this is something many of us scientists are working on this. What are the extremes that can happen? These are low probability events, but if they happen, then the consequences are many, many times more extreme than what's being considered. This is a simulation of what would happen with unchecked emissions by 2100. This is a study jointly done by Princeton and Columbia and NASA. You can see more than half the planet is in severe drought. The entire Amazon, the Southwest, and including California, where I am living, and Chris is already, we are in a mega drought. 12 million acres out of 33 have already burned in California. And India this year is experiencing severe fires, droughts, and others. So this is what motivates us to say, no, we can't let this happen. We got to mitigate, we have to cut down the emissions. I'm just showing you this recent paper published by an Indian group. It shows the extreme events. Entire central India, all the way from east to west, is experiencing threefold increase in extreme precipitation events. What does that mean? Floods, it just leaches the soil. So agriculture is going to be extremely difficult, and with other implications. And this is a map published by UNEP on the fire density, and you can see the entire Indian subcontinent, the yellow region, are moderate fires. Others are severe fires, but all of that will get progressively worse. So I just want to conclude with one major experiment I did with about 250 scientists. About 50 scientists from India joined us. And what we found, India, in addition to the climate change, has a huge air pollution problem. So this was done 25 years ago. And you can see the river of pollution coming from the whole Indo-Gangetic plain flowing into the Bay of Bengal. What we found is dark soot particles from this pollution settles on the glaciers and melting the glaciers on top of the CO2-induced heating. It disrupts the monsoon, and we said this air pollution is what is causing decrease in rainfall in North India. On top of that, 1.5 million die each year from inhalation of this black carbon-loaded cooking indoors. India still has close to 950 million people, because of poverty, forced to rely on 18th century technologies for just meeting basic needs, cooking, heating, lighting. So we found just cutting the biomass cooking, giving them energy access, that's my fundamental thing. In terms of building resilience, we need to accelerate efforts to give energy access to the poorest, about 850 million living in villages. And it's not that they are trying to pollute the planet, they can't afford anything else. So that's the barrier we have to break. And what we just published this paper last year, teaming up with the major groups in India. What is interesting, we discovered, is India can cut its pollution by half. I'm just showing you the maps of India's air pollution. The middle is the winter. Just providing clean cooking through electricity and biogas to the rural households, mind you, that's about 850 million, would cut the pollution by half overnight. So that's, if you can think of a powerful solution. So I took all this, I'm leading up to the issue of resilience. Remember, resilience building has 3 pillars. You need to mitigate the emissions, there's no doubt about that, to reduce the risks. Then you need to adapt to manage the risks, unavoidable risks. And the third, none of this is going to happen without societal transformation. I don't know, my thing is flipping back and forth. Yeah. So mitigate, there are 3 things we have to do. First is all the non-CO2 pollutants contributing about 40% to the heating. We have technologies to cut them down. So US is pushing a major methane pledge. That would bend the warming curve within about 10 to 15 years, cut the rate of warming by half. Then, of course, we need the carbon neutrality, bring the CO2 emissions to 0. Many have proposed this, but none of this is still going to be enough because we have delayed our actions. We have to take out as much as 500 billion tons of CO2. Just to give you a magnitude of the effect, the total solid waste, all the junk we throw in our landfill and garbage, is about 1 billion tons. So it's 500 times the solid waste of the planet we have to remove from the air. So this is my last line. So what do I mean by building climate resilience? I think we have to stop fooling ourselves into thinking we can bend the warming at 1.5, 2. What we need to do is prepare for the further worsening of the extremes by at least 50%. India particularly needs to develop a 10-year climate resilience plan immediately. Its first purpose has to be protect all the vulnerable people from heat waves, wildfires. I have a list of things. I'm just going to leave this, not go through all of them. So I want to come with the issue. In fact, our opening speaker already talked about this. This is a problem I've been working for the last 15 years. Climate justice for the bottom 3 billion. Forced by poverty to rely on 18th century technologies. This is a picture of a village family who hosted me in the Himalayas. And India has about 850 million in this 3 billion. Their total contribution, mind you, contribution of the 3 billion people, that's 40% of the entire planet population. Their contribution to CO2 is just 5%. And we know they're going to suffer the worst consequences, likely 90% of that. human suffering is going to happen in this population. So that should justify investing whatever it takes to give these folks clean energy access. Chris, that's all I had. This is my, if I'd made my talk discouraging, I want to conclude that there is still time. There's still time to protect people. Thank you.
Thank you, Ram, so much for a portrait of a landscape that has many depressing elements. It's really defined by the issues of a changing climate and by the profound issue of social justice, but where there are things we can do. Thanks so much. Our next presentation is from Fiamma Straneo, professor of climate, atmospheric science, and physical oceanography at the University of California, San Diego, the Scripps Institution of Oceanography. Dr. Straneo studies high latitude oceanic processes with a focus on ice-ocean interaction. Some of her most important work involves understanding the way that warm water from the Gulf Stream reaches and helps melt glaciers in Greenland. Dr. Straneo's work emphasizes field studies, usually under challenging polar conditions. Among other honors, she's been named a Bjerknes Fellow and a Sverdrup Award lecturer. Fiamma.
Thank you, Chris. And thank you, Ram, for the wonderful presentation. So let's see, here's my screen. I hope you can see it.
That's fine.
Thank you. And so I'm going to show you a slightly different view, complementary view to some of the amazing science and so societal implications that Ram presented. And what I'd like to do here is essentially two things. One is illustrate some of the consequences of a warming planet, especially with regards to sea level rise and the need to really look at projections for adaptation. But I also would like to showcase some of the work that but also many collaborators have been doing to really try and understand the intricacies of the climate system so that we can inform adaptation. And this speaks especially to the young scientists in the audience, the people who think, are discouraged and there's not anything we can do. There's actually a lot that we can do to improve our understanding, which is really critical to informing sustainability. So my goal is to show you some of the details as well as some of the overarching questions. And I'm pretty far removed from India in my work, but of course, sea level rise has, and in general, cryosphere, ice change has major implications for India. So Ram introduced the warming of the planet. You don't need to hear this again, but one of the things I'd like to point out is that the additional energy in the form of heat that the planet has absorbed as a result of anthropogenic greenhouse gases, most of it has gone into the ocean. And so we have now measurements in the ocean. This is a record that only goes back some 30 years. There's an update now to present time, but about 90 or 95% of the extra energy that has gone into the planet has gone into the ocean. And if this weren't the case, our planet, the surface where we live would be a lot warmer than it is now. And so one of the major consequences of ocean warming is sea level rise. And really, sea level rise, one of the ways we think about it is, yes, there's thermal expansion. In other words, when you warm the ocean, it expands. And that's one of the drivers of sea level rise. But we'll see that ocean warming is affecting many aspects of sea level rise, one of them being the melting of ice sheets. So right now, sea level rise is about 3 millimeters a year. And this pie chart here shows what it is due to in present day, so in the modern day. And the orange sector is about 40%. So this is, again, the expansion of the ocean. You haven't changed the mass, you've just changed the volume. Everything else, the white and the blue, is the contribution from moving ice that was sitting over land in Greenland and Antarctica, but also in the mountain glaciers of the Himalayas, Patagonia, the Arctic, and it's gone into the ocean. And so this melting of land ice is now the largest contributor to sea level rise, and it is also the most unpredictable. And so in the background, I have some of the recent measurements, remote sensing satellite measurements from Greenland that showed this steep decline in mass. In other words, Greenland, like Antarctica, is losing mass. And it's a sizable, as you can see from the pie chart, contributor to sea level rise. So what's happening in Greenland? Well, part of it is intuitive. If I warm air temperatures, I'm going to melt the ice from the top. It will end up in the ocean. And we can do this in models. We understand this. But the other thing that is happening in Greenland as well as in Antarctica is all these glaciers that move from the center of these ice sheets into the ocean are speeding up. And so on the left, I'm showing you an ice velocity map. So Greenland, it's this huge mass of ice, but it's actually moving. And these narrow streams that you see, the red colors, the yellow colors, is an indication of the ice moving to the ocean, to the periphery. And on the right, I'm just showing one snapshot. This is one glacier where I've been working for some 20 years, which all of a sudden in the 2000, it retreated, it doubled its flow rate, and it just was discharging. It still is a lot more ice into the ocean. And so this is happening all over Greenland, and this accounts for about half of the ice loss from Greenland. And in Antarctica, this dynamic change, the fact that ice is moving faster into the ocean, is the driver of much of the ice loss. And this is something that we don't understand very well, that is not in the models, that we need to understand. So when this started happening in the 2000s, one of the key hypotheses is, well, maybe it's the warming of the ocean. And here I'm just showing a map of the ocean currents around Greenland. We have warm Gulf Stream waters, here labeled as the North Atlantic currents, the red arrows moving forward, moving towards Greenland. And we didn't really know at the time, do these waters interact with the ice sheet? And what might they do? And we knew these waters had been warming, but the connection with the large Greenland ice sheet was really unknown. So this is what brought me in 2008 for the first time in this small village of Tasiilaq. And I want to say we didn't have a project funded. We didn't really know what we were going to do. I was traveling with several glaciologists, and it was very much of an exploratory mission. We had an idea, but nothing else. And we also didn't really have funding. So we chartered the only boat we could afford, which is quite small, but with a local driver, a fisherman, who was really instrumental in getting us to the fjord that I'm going to show you in a minute, where the glacier discharges. And so we made some of the first measurements really of the ocean waters at the edge of the ice sheet. And so on the left is the map of the coastal environment, this fjord where we made the measurements. And on the right, I'm showing you temperature profiles with depth. And we went in July, we went back in September. And you'll see that what you're seeing is cold waters. These are water from the Arctics. They insulate the ice sheet. But then at depth, you see these waters that are 4 degrees or so. And this is not warm enough for you to want to go swimming in it, but it's really warm for a glacier. And so you'll also notice it's cold over warm, and this is still stratified, and it's because of salt. And so what we found from this really simple survey was that the waters from the Gulf Stream could get under the cold waters flowing around Greenland from the Arctic and reach the ice sheet. So we'd shown this connection in the climate system, and since then we've shown it in many regions around Greenland, but we still didn't quite have measurements near the glacier, and I'll show you why. So this is some time-lapse camera from the edge of this glacier, and you just saw a big calving event. And I want you to look again at this area, because this is really the region where you'd like to make measurements if you're trying to understand how a glacier and the ocean interact. So everything here that's moving, it's ocean, and the glacier is over to the other side. So we needed to get closer. Again, there isn't a super high technology that can bring us there. It's a rough environment. And so we used helicopters to get even at some of the most basic measurements. So what I'm showing here is flying over a glacier and then looking for patches of ocean water where we can deploy expendable probes that then can tell us what's happening at the edge of these systems. And you're going to see in a minute the zoom out. So we're in a helicopter, we're hovering about these patches of open water, but the scale is humbling. We're very small. These glaciers are massive. This is one of Greenland's largest glaciers, but there are tens of these massive glaciers. And so this gives you a sense of scale, not just of the problem from an ice discharge perspective, but also of observing it. So what did we learn? Well, we learned this is a data plot, but and the glacier is over here, and this is the ocean, and these are the measurements. What we learned is the waters melt the glacier in summer and winter. They get all the way to the glacier, these warm waters. But one of the key things we found is that there was a lot more melting in summer. So we went back, we made more measurements, and we used models. And what we found is a lot of the surface melting that's happening. Remember, there's also rising air temperatures over Greenland. This melting is coming through the ice, coming out at the bottom of the ice in something that looks like this. So this is a plume at the edge of the ice. And this plume is driving even more melting. So it's amplifying the effect of having these warmer waters reach. So this is complicated. It means that not just rising ocean temperatures are affecting the glaciers in Greenland, but also rising air temperatures can affect the submarine melt. And we've, as a scientific community, we've put this together, and it's been a really dramatic increase in our understanding. And so now we can take this knowledge and I should say, I brought up this slide with people because the work is done by people. And this is a very interdisciplinary group. We use chemistry, chemical oceanographers to look at the water masses, engineers and technicians to develop the tools, people from multiple countries. We had Greenlandic residents really supplying the knowledge and support to enable us to make the measurements, postdocs, students. So what about sea level rise? This is a curve. It shows past measurements and proxies, the satellite era, we're going in time, and these are projections, and there are newer projections with different scenarios, different carbon emission scenarios. The thing about these projections is we should look at them, but they don't have some of the physical processes I've been talking about. And these represent major uncertainties in looking forward at sea level rise projection. So we went back, different group, international group, multidisciplinary, a lot of junior people really engaged in the process, really wanting to make a difference. And we put our knowledge in the climate models, and I'm just going to show you what it looks like. So now we understand something about the warm waters going in the fjord. This is now a climate model simulation. You can see the glacier up here is retreating, both due to atmospheric warming and due to ocean warming. And I put this up to show you can go from making measurements in a small boat at the edge of a glacier to understanding the physics that can go into the climate models for projections. And so this is a positive message in the sense of you can make a difference, and sound science really can make a difference. And the last point I'd like to make is when I talk to people about sea level rise and I say it's 3 millimeters a year, this is global sea level rise, and people will say, well, that's not very much. I can live with that. But as Ram mentioned, what we're really worried about as a society is extreme events and sea level rise, as this is a curve that shows the probability of occurrence. of flooding events. This is sort of where flooding begins for this particular location. As you increase sea level, the frequency of extreme events, because you're changing the baseline, the seas are rising, the frequency of extreme events is going to rise. And this is something that really affects coastal communities and through them, the whole of global society. So I had just three messages. One is the climate system is still surprising us. It is both a positive and a dangerous message. There are still many things we do not understand. In many areas of climate science, we're still playing catch up. Observations and monitoring are really key. Observations are knowledge, our power. This is how we know the planet has warmed. And so this is really important in continuing observations. And my last point is the problems are big. We really need collaboration across disciplines, methodologies, nations. We need natural and social scientists to work together. We need stakeholders really to collaborate. And this is a departure from how we've done science in the past. And again, a really important one, and one that is an important message for young people, because it means that you are going to play a role. There's really a role for all of us with all our different expertise to inform adaptation. And I'm going to stop here.
Thank you, Fiamma, for a beautiful example of the way that careful research can lead to really important new insights. Our final speaker is Professor Yadvinder Malhi. Dr. Malhi is Professor of Ecosystem Science and the Jackson Senior Research Fellow at Oriel College, Oxford. Dr. Malhi explores the functioning of the biosphere and its interactions with global change, including climate change. His particular fascination with and a love for tropical forests, though he's recently also been working in savannas, the Arctic, tropical coral reefs, and Oxfordshire's woodlands and floodplain meadows. His emphasis is on how natural ecosystems are shifting in response to global atmospheric change, and how protecting and restoring natural ecosystems can help tackle climate change and help adaptation to the consequences of climate change. Dr. Malhi was elected a Fellow of the Royal Society in 2017, and he was appointed a Commander of the Order of the British Empire in 2020. He's a recipient of the Marsh Award for Climate of the British Ecological Society and the Patrons Medal of the Royal Geographical Society. Yadvinder.
Thank you very, very much, Chris. I'll just share my slides. Okay, can everybody see that? Okay.
Yes, we can.
Yes. Okay, thank you for the intro. So I'm going to cover some of the items that were brought up in Chris's introduction, which is about the role that the biosphere plays, both as a recipient or victim of climate change, but also how working with the biosphere can be one strategy towards mitigating and adapting to climate change, but a strategy that has limits, as I'll cover. So, what a week to be talking about climate change to an Indian audience, as we already saw in Ram's introduction. There are extreme conditions in much of India, and this is not just a short 1 week heat wave. If you look at top right, this has been persisting for quite a period now. And there's a part of climate change science which tries to attribute extreme events to human causes. And I'm sure we'll hear sometime in the next month or so the first of these attribution studies coming through. And almost certainly they will say that human-induced climate change is a big factor as a cause of the current extreme conditions that we're seeing in India. And with increased warming over this century, these extreme events sitting on top of a warming trend, these types of extreme events are going to become more and more frequent. So India truly is at the front end of climate change impacts. And this has many consequences for people living in India and other regions, but it also has consequences for the rest of the biosphere of India, the other species that exist in that region. And those extreme conditions make it extremely difficult for many animals and plants to cope in the medium term, which has consequences both for crops but also for wild ecosystems, and also the effects of these ecosystems can then further degrade the local climate and feed back to enhance the effects of climate change, both locally and globally. And we, as was described earlier, we know that the climate change is caused by greenhouse gas emissions, and carbon dioxide emissions are significant, although not the only component of that greenhouse gas rise. And carbon dioxide emissions are dominated by the combustion of fossil fuels, and land use change, the degradation of the biosphere, was a significant part of the overall pattern, but in recent years has been dwarfed by the fossil fuel component, though it is still around 10% of our emissions come from deforestation and other forms of degradation of the biosphere. And of all this carbon dioxide that's pouring into the atmosphere, as I said, around 90% of that from fossil fuels, only just under half of it ends up as a rise of carbon dioxide in the atmosphere that causes the greenhouse gas effect. Around a third of it ends up being absorbed by the land biosphere, partially through regrowth of the biosphere, partially perhaps the extra carbon dioxide stimulates the growth of plants and increases their biomass. And about a quarter of it ends up being absorbed in the oceans, where it's a carbon sink, but it also contributes to problems such as acidification and the damage that's causing to ocean ecosystems. But this 30% going into the land biosphere, if you think mainly into the forests, is significant. If that wasn't happening, the rate of climate change would be even faster than it is now, and our chances of staying below, say, 2 degrees of warming would be even less. So another way of thinking about this is in terms of the remaining carbon budget. How much carbon dioxide can we emit before it becomes more 50% or more likely that we'll reach a certain peak temperature? And we only have around 420 gigatons of carbon, around 11 emissions under the current trajectories, 11 years of emissions before we pass the 1.5 target, or we have about 30 years before we pass a 2 degrees peak temperature target. But many of these projections assume that the biosphere keeps on absorbing carbon as it has been doing over recent decades. If this biosphere carbon sink gets weaker for any reason, because of climate change or other factors, then that remaining carbon budget we have, that little space we have to try and stabilize our carbon emissions, gets less. So the fate of the biosphere is very important in determining the challenge that we face this century as we try and get our emissions down to zero. And the biosphere itself is a victim of climate change in many aspects. So this figure shows how under a medium-high warming scenario, on the right a medium-high one, on the left a medium-high one, on the right a lower warming scenario, how much of the biosphere will start experiencing novel climates that are not experienced on Earth at the moment, or disappearing climates that exist at the moment that will no longer exist on Earth under that climate change scenario. And you can see quite significant areas either moving into new climate regimes or having their existing climate regimes disappear from either their region or from the face of the Earth. So we expect large changes in the biosphere and the species over this coming century. And there have been a number of estimates, and how does this translate into risk of species extinction? And this figure shows that it's very hard to quantify that risk. It depends on which species you're looking at, what approach you take, and there's a huge amount of variation. So each of these blue points here is a estimate of perceived percentage extinction, a published study that estimates percentage extinction under a certain degree of temperature warming. So you see under about 1 degree now, there's a few studies here, but projecting for 3 degrees warming, we see a range of studies with a huge amount of variability. Some of them saying around 5 to 10% of species would go extinct, which is still a huge number. some going up to around 40% of species, which would be absolutely devastating for the Earth. And you see that the risk of species extinction goes up the warmer temperatures get, which is why the targets of Paris are to try and stay well below 2 degrees in terms of overall warming. Because that matters not only for the species themselves, but if we start losing significant components of the terrestrial biosphere, this feeds back to the climate change system itself. The biosphere acts as a buffer that limits the degree of impacts of climate change. And if the biosphere starts weakening, those impacts become more severe. And the uncertainty in the carbon emissions from the biosphere is one of the greatest uncertainties in trying to project future climate change. So on these two figures show projections of the flux, the sink of carbon dioxide into the oceans and to the land from a range of models up to the end of this century. And you see that the oceans, there's an increasing sink over time as the CO2 in the atmosphere rises. But there's some uncertainty. But on the right, if you see in terms of land, and each of those lines is a different model, you see that there's quite a lot of uncertainty. Some models say that the biosphere will keep absorbing carbon dioxide and slowing down climate change, but other models say that this carbon sink, this brake on climate change, will weaken or possibly even reverse, so that the biosphere becomes an accelerator of climate change. And that would be a dangerous point where there's a risk of runaway climate change, whatever we do without emissions. And scientists have identified a range of sensitive areas of the world, which are sometimes called tipping points, where the bits of the biosphere may be most vulnerable to significant climate change degradation, that at a scale that could feed back to atmospheric change and the rate of climate change itself. And one of these, the one that I've worked on quite a bit over parts of my career, has been the Amazon forest, one of the most important parts of the biosphere, terrestrial biosphere in terms of its function. And this has been an area of study looking at what the risks that the Amazon forest could start dying back significantly and start releasing carbon to the atmosphere. So the challenge we face is how do we think about the biosphere in the context of such change? And one diagram I often like to use is this one of a bottleneck. And what this bottleneck presumes is that we will fundamentally get round to tackling the climate change problem, that at some point, hopefully sooner rather than later this century, we will get to net zero emissions and will stabilize the climate at hopefully below 2 degrees of warming or in that vicinity. But in the meantime, we've got intense pressures of a warming climate, increasing extreme events, plus degradation, land use change, and other components before we get to this new future stable climate. So the challenge we face is to maximize the functionality of the biosphere. This is what we face as people interested in the biosphere, like ecologists like myself, is in maximizing the resilience and stability of the biosphere. So it both contributes to adapting to climate change and mitigating climate change. And also, once we get through this bottleneck, that we have functional ecosystems. They'll be different from the ecosystems of the 20th century, but they could still be functional, or alternatively, if we fail in this task, they could be greatly diminished and degraded ecosystems. And these interventions are what motivates me as an ecologist in thinking about ecology in the 21st century in the context of climate change. And so one approach to tackling that question is through what's now commonly called nature-based solutions. To what extent can we address the climate change challenge by either protecting nature or by restoring or enhancing the functionality that nature provides? And that's important both in addressing climate change, but if we get it right, we can also protect biodiversity, restore biodiversity on the earth, and also, if we do it right, enhance livelihoods for the rural poor and for many other parts of the global population. So nature-based solutions are not just about tackling climate change, but also doing it in a way that's ethical and just and is good for biodiversity. And nature-based solutions in terms of climate change can be as much about adaptation as they are about mitigation. So clearly a shaded tree-lined street like this is much better able to provide people the ability to cope with the intense heat events we're seeing in India than an open, barren, concrete urban jungle. Trees on slopes can lessen the, in this case in an agroforestry context, can lessen the risk of extreme flood events and associated damage. So adaptation is definitely a key part of where nature-based solutions can contribute. But in terms of mitigation of climate change by absorbing carbon from the atmosphere, they can certainly play a role. And broadly, mitigation activities can be in terms of protecting intact lands, so protecting remaining forests or wetlands, better managing working lands in terms of farming better, having more agroforestry, managing grazing better, but also restoring native cover where we can, restoring forests and wetlands, for example. And so what's the maximum contribution that nature-based solutions could make to tackling climate change? This figure from a paper we had last year gives you some idea of the potential there. So the purple line here is the current trajectory in terms of where we're heading with global warming. The blue line here is a 2 degrees peak warming scenario, and the 1.5, the light blue line is a 1.5 degree peak warming scenario. And the dashed blue line shows what different an ambitious but feasible global strategy for nature-based solutions could have. So what you see is that the dashed lines, they can have a modest effect on the peak. And for the 1.5 degree scenario, it's only a modest one because we haven't got time to scale nature-based solutions at the scale we need to at this time scale. But they can continue to absorb carbon after the peak and therefore affect the rate at which the planet cools down as it needs to after peak temperatures. And so nature-based solutions can certainly make a contribution, but look, also they can't solve the problem. Ultimately, the problem can only be solved, we can only go from the purple line to these blue lines by reducing greenhouse gas emissions. So the fossil fuel combustion has to be the primary issue to tackle. On top of that, nature-based solutions can make some contribution to that mitigation challenge. So how much land is there available for nature-based solutions? So I'll just show one example of how we can look at that in the context of India, which is looking at the potential to restore forests in India. And India has particular challenges. This is a map of how much of the biosphere's productivity is used for human use in different parts of the planet. So you see areas such as the Amazon with quite low human use overall. And India is up there as some of the most heavily used land on Earth in terms of supporting a large rural population, large urban centers, and a long history of using the land. So India presents particular challenges for nature-based solutions and restoration. And this is quite a long history. This is a study I did with a student a few years ago where we looked over 400 years of records at how land in India has been used, the intensity of land use in India. And you can see even in 1700, large areas of the Ganges, of the Punjab, of Maharashtra were quite heavily used and from a long history of agriculture. And that expanded further in the 20th century with the industrialization of India and the increase of population as well, to show that large parts of India are very heavily used. There's only some areas in green there having significant amounts of semi-natural landscapes. And so in this study, led by my student Trisha Gopalakrishna, we tried to estimate the total potential area of forest in India, which is around 100 million hectares, and then factor out various factors about what of those forests, what of that land is currently not forested and has potential for being used for forests. And each of these numbers is lower than the original as we keep on bringing out factors to work out, firstly, the maximum biophysical opportunity in India, and then areas that we can't use, areas covered by national highways, by irrigated crops, by croplands, and census towns and villages. And then we ended up at an estimate of how much land was potentially available for reforestation. There's a lot smaller than is often widely reported as the potential area for land in India for reforestation, around 1.5 million hectares. So not insignificant, but much smaller than we often assume by looking at global studies, but because of the intensive history of land use. So this map shows where the opportunities lie, maybe in this central eastern parts of India in particular, and also around Assam and in the mountain regions around Uttarakhand, maybe where there's maximum opportunity for nature-based solutions focused on forest restoration. So what can be done in India? There's only a limited potential to expand native forest cover. So I think we need to look at, we need to protect existing lands in India, but also need to think about how we can better manage working lands in India to enhance carbon stocks and also resilience to climate change. And another study looked at a range of countries and looked at which of these possibilities, whether protecting land, managing land better, or restoring ecosystems was the best for different opportunity for different countries. And where we see India is up here in the top as an area where there's limited potential for restoration of forests, but there's substantial potential to manage agricultural lands better. For example, as in this photo on the right, through agroforestry, that can also improve people's livelihoods, improve their resilience to climate change, especially under extreme temperatures, but also absorb carbon and potentially gain revenue through absorbing carbon that can provide that can further improve, mitigate climate change, but also improve local livelihoods. But we mustn't overstate the potential of nature-based solutions. It's very easy to think, well, if we plant trees, we're doing something for climate change. And if so, everybody loves trees. So by planting trees, we can solve the problem. And when certain political leaders who have been very negative on climate change action love trees, then you know there's something dangerous about trees as well. And that is that we shouldn't use an emphasis on nature to distract from the fundamental challenge, which is to deal with fossil fuel emissions and get fossil fuel emissions down to zero in the next few decades. And that remains the fundamental challenge, where nature can help, but nature can't be the main solution. So just to conclude, the biosphere has been acting to slow down the rate of climate change, but it really is uncertain how long this carbon sink can persist. And a weakening biosphere will enhance the risks of dangerous climate change. And India is at the front line of climate change impacts, both on its human and its non-human populations. Nature-based solutions, such as enhanced tree cover, can help India adapt to climate change and make a small contribution to mitigating climate change while enhancing rural livelihoods and biodiversity. But nature-based solutions are no substitute for rapid decarbonization of energy, industry, and transport. This needs to be done certainly in the global north, which has contributed the majority of climate change to date, but it also needs to be done in the global south, in nations like India, to move from a fossil fuel intensive future to one that's based on renewable energy and low carbon emissions. So, thank you.
Thank you, Yadvinder. Spectacular portrait, both of challenges and opportunities. And thank you also to Fiamma and to Ram for really laying out a spectacularly clear landscape of the challenges we face, but also the opportunities. We now have about 45 minutes for a discussion, and I'm looking forward to hearing from all of you with some more details about some of the aspects that are so interesting and so compelling. I also want to point out that this is an opportunity for audience engagement. I'll spend about half the time with conversation among the panelists and questions from me, but the other half with questions from you. So please think about the questions that you would like to hear the panelists address and put them into the question portal, and we'll get to as many as we can. Let me start with the issue of tipping points. We've heard several references to the idea that as a result of melting glaciers or of loss of the terrestrial carbon uptake, we might hit a point at which our ability to manage climate change really erodes substantially and rapidly. And I wonder if each of you could give a sense of how you see the risk of these major tipping points unfolding as the global average temperature continues to increase. And in particular, I'd be interested in how you see the risk of tipping points relative to the widely discussed 1.5 degree, well below 2 degree targets. Fiamma, do you want to start with that?
Sure, but I don't have any answers. From the perspective of the cryosphere and maybe the ocean, there are tipping points that have been hypothesized, proposed, that we should be worried about. The West Antarctic ice sheet, because of the ice dynamics, is poised to potentially lose large volumes of ice over relatively fast timescales. When I say fast, I mean hundreds of years, as opposed to the thousands or 10,000s that we'd expect. Greenland, as it lowers, as the ice surface goes down, again, there's warmer air coming in, has the potential to accelerate. And then we have the Atlantic overturning circulation of the ocean, which we know in the past was in a different configuration. And so these are all some of the tipping points. I think the way to think about tipping points is that we should always consider them as events that might happen. We do not know enough about the dynamics now to have any certainty about them. So it comes down to making decisions that take into account that they are a possibility, while at the same time maybe working on some of the challenges we already see. So the science cannot predict exactly, will we hit these tipping points, when, and will they even happen? Because as I tried to point out, there are mechanisms in our climate system that we don't fully understand. And this is not to say the planet isn't warming. This is not to say the planet will not continue to warm. Sea level will continue to rise. We know this, but the tipping points are thresholds, are very nonlinear dynamics that we do not have the tools to be certain about. So I guess the solution here is to definitely act on what is already happening, which is very dramatic as it is, while at the same time consider the possibility that we are heading for even more dramatic change in the future that might have these non-linear major response implications.
I wonder if I can follow up with one aspect of sea level rise that strikes me as really worth increasing our understanding of. And that's the idea that at some level, we become committed to large amounts of sea level rise, even if greenhouse gases drop to zero, and even if we eventually cool the climate. And could you give us a little insight into how well understood this hypothesis of marine ice sheet instability, or of the other mechanisms that could drive this kind of commitment to large amounts of sea level rise in Greenland are?
Right. So this doesn't, what you mentioned, Chris, does not really require a tipping point. In other words, the ice sheets change over longer timescales, and once you set the ice loss process, if so you will, in motion, once the atmosphere, for example, has warmed, there is a progressive and continuous ice loss that will continue for a long time, because we've changed the dynamics of the ice sheet even without getting to a tipping point. And so we are committed. Another way to think about it is some of the changes that are induced by ocean warming, we haven't even started to see yet, because some of the heat that's gone into the ocean is stored in different parts of the ocean, different depths. It hasn't reached the ice sheets yet. And so this is a change that we're committed to, that does not require tipping points. And this is part of what I was arguing. We should be acting on what we do know, and there's a lot that we know So yes, so some of the processes, some of the feedbacks that happen with warming of the ocean and the atmosphere and affect melting of the ice, some of the dynamic responses have been set in motion. We just haven't seen the effects yet. So some of the glaciers, ice streams in Western Antarctica, we are starting to see their speed up, but the response time is so slow that it will take them hundreds of years to respond to the changes that are happening now in the atmosphere. And the same is true for Greenland. And yeah.
Great, thank you, thank you. Let me stick with this tipping point theme and go to Yadvinder, who you already spoke a lot about the risk of decreasing the strength of the terrestrial carbon uptake or converting that to an increase. And of course, the concern there is, again, even if anthropogenic greenhouse gas emissions go to zero, if the biosphere now becomes a source, warming continues. And what do we know about the risk of that and the temperatures at which it might be activated?
It's just to reinforce the point just made. I think tipping points help reflect our uncertainty of the knowledge of the Earth system. So we can broadly sense that there are potential danger points in around Amazon dieback or permafrost release, but the detailed dynamics of that are always going to remain fairly uncertain. There's so many processes involved. And when we frame a temperature of 1.5 degrees as being a relatively safe peak to head for, it's framed in the sense of saying, well, we're expecting most things to be linear in the Earth system until that point. But once we start going beyond 2 degrees, there may be sneaky surprises, either the ones that we're already thinking about in the biosphere, or even other tipping points that we haven't even thought about now that may begin to emerge. So I think this tipping point framing helps us understand why 1.5 or 2 degrees is so important as targets. In terms of significant risks, I think the ones that get most attention are potential tropical forests dieback, like a large-scale loss of the Amazon through a mixture of land use and fire and climate change. And at higher latitudes, the boreal forests or the permafrost, the vast amounts of carbon stored at high latitudes. And all of those are, I think our science has improved over time. Often these predictions come first from models that are necessarily simplistic. They're just trying to incorporate these elements into Earth system models. And then once those models come up with potentially alarming predictions, then a lot of further research goes in to try and understand the details of the mechanisms. And I, for example, have been involved in research and simulating drought in the Amazon through experiments to see how resilient or not trees might be there. The final thing I'd add is, unlike, say, some of the other tipping points, such as in the cryosphere or in the oceans, the ones on land are intimately linked to one other process beyond climate change, which is land use. And so how people interact with the land can either enhance the risk of tipping points or alternatively reduce the risk. So there is a separate, we're not purely in the fate of the wheels of climate change when we think about terrestrial tipping points. For example, in the case of the Amazon, we know that fire plays a major role of interacting with climate change to cause loss of forest. So if we can come up with better fire management strategies, ways of buffering against fire, better regulation of fires, they may help avoid or navigate away from tipping points that climate change may be driving us to.
That's a really, really important point. Yeah, thanks for closing with that. That actually gets to the aspect of tipping points that I wanted to ask Ram about. You spoke so compellingly about the opportunities for adaptation. And I wonder if you could say a few words about the way you see adaptation and greenhouse gas emissions interacting, because as Yadvinder's already described, there are really important roles where human activities interact in important and not necessarily predictable or linear ways with other carbon cycle processes. And one of the things that's always struck me is that when we mobilize society to tackle climate change, we need to have enough social coherence in order to be able to do that. And populations that have adapted effectively are likely to have more ability to work collectively.
Yeah, just one brief point on the tipping points, Chris. I'll come to this issue. This is something all of us, atmospheric scientists, do with climate models. We will double the CO2, then we will quadruple, we'll increase it 8 times. And it's perfectly linear in our Earth's 3-dimensional climate models. They have no glaciers, they have so-called all the physics. So I think we can't rely on our models on these, on this tipping point issue. One. The second thing is we held a meeting on this issue at the Vatican 8 years ago. Kurtzen and myself, we were looking at the Himalayan Tibetan glaciers. And they were melting more rapidly than other alpine glaciers, except the Alps. So what happens is that when the glacier is melting, downstream there is more water. So you're going to have a hard time persuading people this is bad for you. It turns out in those Tibetan Himalayan glacier models, there were also Chinese scientists, Indian scientists have done a lot of work on this. It turned out after you lose 50% of the glaciers, then it's rapid, it's gone. So these type of issues are lurking out there. You know, Tim Lenton from Leeds is one of the active people in Tipping Point. So I'm glad you raised this question. I think we should resist the temptation to rely on our IPCC type analysis of this. They rely mostly on our 3-dimensional climate models. On the adaptation issue, I think it's a fantastic question you asked. Is that now there is a major movement within the modeling community, the so-called integrated assessment models, as to bring in, finally they're asking the question, where are humans in our climate models? There are no human behavioral change interactions. So that is being now factored in interactively. We ourselves have a paper on this in Nature about last year. What that is showing is evolution of climate scenarios very different from what this IPCC with this SSP, you know, their whole scenarios of future, because they don't allow that interaction. And so now that sets the stage for me to, on the adaptation. This is a study we are doing, you know, with several others. If you don't provide energy access to the poorest 3 billion, in another 10 years, the warming becomes so oppressive for them, both in terms of doing agriculture and in terms of meeting their basic energy needs. So they burn the only fuel available to them. The forests will be gone with fires and all that. So they could rely on fossil fuels. Because they need energy to cope with this. So we find then the fossil fuel consumption for this 3 billion would overtake anything else we are doing, surely because of our negligence. So I think that is why we need a major push on bringing adaptation and mitigation together, because adaptation is going to impact the mitigation because it requires energy to adapt. Just where I live in Southern California, we never had air conditioners. Now there is a major push for everyone to have air conditioning. So that is a major issue. In fact, social scientists, particularly at John Schellenhuber's Institute and Rockström's Institute in Sweden, the environmentalists, they're looking at the so-called social tipping points, where the behavioral change can be changed abruptly. And I want to bring in the point, one point I skipped through in my slides. Remember, I said resilience needs adaptation, mitigation, and societal transformation. And we need a massive education program. I'm not talking about climate change 101 or things like that we teach in universities. I'm just talking about educating the public. What is to come? And just take the California agriculture. We are in a mega drought. They're thinking it'll go away. I talked to the people in Central Valley. They're thinking it's part of variability. We always had droughts. It'll go away. It has not got into their psyche that this is a trend. We are looking chronic trend. It's not episodic. And the same thing with India. I think I spent 6 months sabbatical in Indian villages. Those women walk about 2 kilometers every day to get water. So if you have a drought, instead of 2, they have to walk 5 kilometers. That will pretty much do them in. So anyway, I think it's time we bring in the adaptation, both in terms of policy and in terms of the science we are doing. I think Fiamma made that point beautifully. We need to bring social scientists into this.
Yeah.
They are coming in, not in enough quantities.
I'm really glad that you raised the concept of social tipping points. I think that provides a really nice framing for the importance of thinking about people in the system, but it also raises the possibility that a tipping point in the way a problem is conceptualized or addressed could go in a positive direction as well as a negative direction. And one of the things we need to think about is how to create a landscape in which positive social tipping points are the more likely outcome. Let me swing back to an issue that all three of you raised in your comments that I think is really fundamental to the evolving understanding. And it's this question of whether the Earth system, including the people, tends to behave in linear, predictable ways like the models have tended to show, or whether its non-linearities and unpredictability, or things that we're not predicting yet, that really dominate the picture. And how should we adjust our thinking in order to accommodate the processes we don't yet understand and the aspects of the dynamics that are lurking behind the current status of sophistication of the way we can model these processes. Fiamma, do you want to start with that? I know that ice is the classic case of having unexpected hidden dynamics that turn out to be the real important drivers.
Right. So to summarize, maybe for all those who aren't familiar, though we probably all are, but the idea here is what Ram was describing, this linear change is every time you push a system a little more, it moves a little more. And the nonlinear changes we're talking about now means when a small change can produce a large outcome or a much larger change. For the glaciers, it would be a small increase in ocean temperatures or air temperatures, like I described, can produce a really large loss in ice because of these, we call them nonlinear, but these dynamics with feedbacks that emphasize. And so my best answer is this is a complex problem, and we need to go at this question from many different directions. So in what I do, observations have led the models. We see changes that were not predicted, and then we rush to understand what happened. And so observations are key, but at the same time, we do not always have enough observations, data to inform our understanding. And the models are then key to explain. You can include the physics. The observations tell us what physics, chemistry we should add, and they explain why things are happening. So this is why I strongly emphasize for this breakdown of some of the barriers that exist to addressing science, especially the physical science in isolation. We really need all of these components, and it's only through the bringing together of the modelers, the observationalist, the chemist, the atmospheric scientist, and that we can start to see the different pictures come together. And again, the social scientists and the stakeholders here are very important, because we have finite resources, even in research, especially in observations. And we have to make some choices about which questions we might need to prioritize, at least for some of our science, and engaging with society to understand what are some of the most urgent questions is also really important. So I haven't answered the full question about nonlinearities, but sometimes we don't have the physics in the model to know where the nonlinear thresholds or the nonlinear amplification will come from. Problems like permafrost, which I didn't mention, but Yadvinder mentioned, it's really an unknown. We don't fully understand how much increased carbon, methane will be released by permafrost. So we need this concerted effort, observations, models. While we study it, we also have to look at what is the impact of melting permafrost, even on the local people, because there's a global impact, but there's an impact on communities. And the same science can inform whether communities need to be relocated because the ground is no longer supporting the houses where they're living because of coastal erosion. And so there are many aspects to these problems.
And Ram, I'm going to stick with this theme for a second. You showed the figure of a prediction that we reach 1.5 a decade earlier than the IPCC projection, and there are lots of examples in climate science of where revision points to impacts that are earlier or more severe. There are a few cases where we see it go the other. I would say that most it's in the direction of underestimating severity with the first passes. And I wonder if you have a general philosophy of how to think about adding a buffer or a precautionary margin to our projections to accommodate this common experience that as we learn more, the detailed mechanisms tend to, I would argue, on average, indicate that the problem's more serious than we thought initially.
Yeah, Chris, I subscribe to that the models were phenomenally good in predicting the mean temperature, the whole globe, but they did not anticipate any of the extremes we are experiencing locally and regionally. And you can quickly blame it on the fact that the model's resolution is pretty coarse. So since about 10 years ago, I started not relying on models for the extremes, but rely on the data. And it so happened that when the planet crossed the degree warming around 2014 to 2015, it's in the last decade to decade and a half, the extremes became so visible in the data that you can attribute it. So this signal became larger than the noise as far as the extremes are concerned. And if we assume the most conservative linearity with warming, that the extremes are linearly related to the warming, then you can come to the conclusion either the intensity of these events or the frequency of the events could increase by 50%. And the area I'm studying is California, purely for selfish reasons. I live here. Like I said, our forest area is 33 million acres. As of 2018, 11 million acres are burned. And 2020 alone, when we were in the middle of the COVID crises, California, 4 million acres burned. That's 14% of our forest area. So I was thinking of, as I was listening to Yadvinder, if this phenomena is global, then the land 29% uptake of the CO2, how much is that going to decrease? So in terms of the buffer, there are two avenues I'm pursuing, with the California government and little bit with the national government is that we need some mechanisms to quickly reduce the warming. Okay, and that's why we came with the short-lived climate pollutants, methane, hydrofluorocarbons used as refrigerants, and increase in the tropospheric ozone, which is a major greenhouse gas, and soot from diesel. And we know how to cut them. For example, California has now said by 2035, all the new cars will be electric. That will get rid of the diesel. So if we cut these pollutants, my own work and then work done at Duke University and few others, find that we can cut the rate of warming by half from now to 2030s. Because of this, US, Biden proposed the Methane Pledge. So that's starting. And right now there is a bill, both Republicans and Democrats support this bill. It's not been advertised, that we will ban HFCs. HFCs will be regulated because there are other refrigerants. The thing about the short-lived climate pollutants is that we know how to bring them down, except for the methane emissions from cattle. Okay, that's a huge agriculture problem we are not figured out. Third of the methane escapes from gas pipes. I mean, it's ridiculous. We should be able to maintain these pipes, not to leak.
This is valuable stuff that's leaking out. Yeah.
Exactly. And the other thing is that America throws 40% of the food, processed food, into landfills, and they become methane. So all we need to do is take that food, put it into a biodigester, convert it into renewables. Factor of 25 of the methane warming is gone. And I think that is something all Americans, I would think, would support, not throwing food into garbage. So these are issues we can get people to buy in. But then at the same time, I'm fairly convinced, Chris, I think I'd be alive by 2030 if my prediction comes true or not. I'm fairly convinced the degree and a half warming is upon us, give or take about 3 to 4 years uncertainty because of natural variability. So it could happen as early as 2026, 5 years from now, or as late as 2035. My worry is we are now going to be involved in the Ukraine war, and then the COVID, we have to recover from it. This thing would land on us. So I think the other buffer I'm pushing hard, I've not been successful so far, is a climate education for all, where we educate people, the masses.
Yeah, it's super important. And I think your concern about passing the 1.5 target, it is come into new focus as a result of the conflict in Ukraine, and it shows how politically unstable the commitment to tackling climate change is, and at least in the US, how climate really left the political narrative almost entirely. Let me just close up with one final question to Yadvinder before we leave this issue of, before we leave this part of the discussion. There are a whole bunch of fabulous audience questions. And you illustrated the substantial potential of nature-based solutions, both for adaptation and for mitigation, but with a really important note of realism about all of the other competing uses on the land and the reasons that the really high estimates in India are more optimistic than we can expect. And one of the things that I get the impression is that around the world there's been such great enthusiasm about nature-based solutions that sometimes it takes the eye off the ball of the importance of tackling the industrial greenhouse gas emissions. And you spoke to this point in your comments. And what are your thoughts on how to manage that tension between nature-based solutions being real and important, but far from the entire solution to the problem?
Yes, thank you. I think that's a really important point. And I guess the approach is a little bit what I just did in my talk, which is to to emphasize the importance of nature-based solutions, but to always have that caveat in here that the major challenge is fossil fuel emissions. And there's a danger. We see so much around how companies or countries are saying that they're tackling climate change, and they show pictures of countryside or trees or nature, implicit in that is if we have more trees, if we have more countryside, we're green. And that can deflect attention from the fundamental issue of fossil fuel emissions. So, as scientists, I think always having that caveat that I had in my presentation, but also making sure that when businesses or countries, when they're talking about their nature strategies, or carbon offsets or whatever, or similar terms, that we question them. How is this part of your overall strategy of getting to net zero emissions? That it isn't just we're planting some trees so we can continue business as usual, whether it's academics going to conferences or whether it's countries coming up with their carbon emission strategy. That nature-based solutions are one of the strategies over a range of strategies that get us to zero carbon emissions.
And I think an important point that each of you has raised is that there's not going to be any single approach that solves this problem. If we're going to tackle it effectively, we're going to have to tackle emissions, we're going to have to tackle education, we're going to have to tackle natural climate solutions, we're going to have to tackle increased investment in research so that we can understand where some of these hidden dynamics are. This has been really fabulous. We have 15 minutes or so left, and I do want to get to some audience questions. The first one is probably for Fiamma, but you all might want to comment on it. So the question says, many tropical rivers are carrying far less sediment to their estuaries and deltas and coastal waters due to upstream dams, enhancing risks from sea level rise. Experiments to manage reservoirs and dams to release sediment are constrained by design and current policies. Is there scope for alternative management of reservoirs and dams? And how much of a factor is the way we manage the terrestrial hydrosphere related to risk from sea level rise? And I realize that's sort of linking the cryospheric components with the terrestrial components.
So I do not know too much about dam management, but I guess but I do know a little bit about one of the largest challenges from sea level rise is infiltration of seawater into groundwater that's used for agricultural reasons, or water that is used for drinking. Or there are also major issues with sea level rise and sewage disposals, which then will impact the coastal system. And so this, together with dam management of reservoirs and shifts in sediments carried, they're all very complex problems that I think, again, we need to take some of the predictions and knowledge. And when I say predictions, I do not just mean climate model predictions. As Ram said, the climate models have very large grids. They're good at predicting global climate, but there are many strategies to get at regional predictions. So taking into account the changes that we know are going to happen, as Ram said, we know drought will persist in California. We don't really need super accurate models for that. We need the models maybe to decrease the uncertainty, but we know drought will persist. So management of our coastlines, management of water resources needs to take into account, for example, the possibility that increased extreme storms might dump large volumes of water, and these might become more frequent. That coastline change will affect the sediment transport of the deltas and move sediments in different areas that might, again, affect humans' ecosystems. So my answer here is really, again, to bring the engineers, the coastal planners, with some of the scientists that are studying the ecosystem together in the planning phase, so that we can prepare as opposed to react, which I think is where we're mostly at now.
Thank you. Yadvinder, as our terrestrial ecologist, do you want to comment on sediment transport and its role in coastal dynamics?
Not something I have particular expertise in, but certainly I think the more we have intact semi-natural ecosystems, the less soil erosion there is, and the loss of topsoil into rivers and ultimately into the marine system can be inhibited. So the degree of soil erosion is certainly a major part in both weakening the ability of the biosphere to grow or to respond to change, but also ends up causing significant losses to changes in aquatic and marine systems.
And this is a really nice example of a potential knock-on effect where well-intentioned infrastructure that's often critical for food security through irrigation can have, unintended negative consequences. We probably have time for one more question, and I'm tempted to try and combine two questions from the audience here into one that I hope each of you would be interested in addressing. The first is that many people feel that COP26 led to the most recent update on the Paris Agreement. Many people believe that COP26 failed when it comes to climate justice. And where are we in integrating the critical issue of climate justice with the equally critical issue of delivering climate solutions? And kind of in that context, the last question I hope people can address is, if you were to advise young researchers and early career scientists, what would you say are the major unanswered questions, but also more broadly, the major themes that they should be focusing on if they want to help move the needle on this critically important topic? Ram, the climate justice one kind of started with you, so maybe you could begin the comments.
Yeah, I think the climate justice issue really got a major attention in the IPCC Working Group 2 report. I think, Chris, you used to chair it.
My old group.
They really bring that very clearly. But where I see the issue is not much discussion of this when they try to craft the policies of mitigation, because the focus is excessively on mitigation. And I think the wrong-headed thinking there is that mitigation is independent of adaptation. So if you bring that thinking into them, that adaptation would involve energy consumption, would involve more CO2 emissions, maybe the two would be coupled. So the simplest answer is scientists now, both natural scientists and social scientists, fully recognize the climate justice issue. But it's not translated into the policy. But Chris, I have one worry about if we focus excessively on the climate justice issue, the rest of us, I call us the top 1 billion, contributing 60% of the emissions, we may think, oh, this is just a problem for the poor. I don't have to worry about this for myself. So I worry about that effect. We would leave half of America behind thinking, oh, this is a problem for those who are living in the slums and poor nations. I don't have to worry about this. So it's a two-edged sword.
Yeah, it's super important to recognize that climate justice is also about energy access. It's also about technologies to decrease the kind of indoor air pollution, real crisis that you talked about, and to think about. I love the picture that Yadvinder showed of the tree-lined streets and the implications of having the flexibility to implement common sense, often quite simple parts of the solution. Yadvinder, do you want to follow up on sort of what level of technology is needed and how that plays into the climate justice? And also, if you do want to comment on where young people should be focusing their efforts to advance this agenda as effectively as possible.
Okay, yeah, I'll answer on both. So on the climate justice issue, I was in Glasgow, as is nearby for the climate conference. And I think the big failure of climate justice there is simply the resources, the financial resources that were promised by the rich countries to the poor aren't being delivered. So we're expecting the big ambitious emissions reductions, but the promises for resources get ignored, the failure in promising the resources. So it is important to always keep that pressure up to recognize that climate justice issue and to get those resources that can facilitate the transformation. Having said that, that focus on climate justice shouldn't be an excuse for paralysis for countries of the global south to act on climate change now. Because as we can see with the heat wave in India this week, India is already suffering the consequences of climate change, and it's in India's own interests to tackle the issues around pollution, to divert from a pathway of heavy fossil fuel use to one of renewable energy. And there's probably economic and multiple health benefits that come through it anyway, irrespective of that. And then certainly we need the resources to make that happen. But I see, with enough willpower and enough defeat of vested interests, I see no reason why India couldn't be a renewable energy superpower in terms of providing the energy resources that its people need without burning coal in vast quantities. So the transition needs to happen, and it needs climate justice, but it shouldn't be dependent on climate justice. I think it's important for India to do this irrespective. In terms of what people should focus on, I'd say, well, as we've seen, there's so many dimensions of the problem, from governance to local solutions, urban solutions, rural solutions. And so there's multiple fronts which people need to engage in. But I would say to the young, engage with positivity. Sometimes it's easy when you hear these stories to sink into despair and gloom as to where we're heading. But I think there's also a huge opportunity to make a difference at multiple scales. And this is the challenge of our century. And I think the next generation are up to the challenge of meeting that by engaging positively and finding pragmatic solutions to the challenges we face.
Yeah, that's a really inspirational way to think about this. Thank you so much. Fiamma, do you want to comment on the question of the roles for the next generation of climate scientists and climate solutions practitioners?
Absolutely, and I agree with what Yadvinder just said. There's lots of opportunities and a positive attitude, an attitude of we will find solutions is critical here. And I think personally it's a really exciting time to engage with the climate problem, both from a scientific perspective, but also from a solutions, be these engineering oriented, but also a lot of them are integrating solutions that, in a sense, nature found by itself, and the appreciation of observation for incorporating solutions that we already see in the natural world that take advantage of what ecosystems, trees do already for us. So in a sense, it's a really exciting time, I think, for scientists, because we've realized maybe climate science used to be only happen in academia, only happen in the universities. And really now, how we deal with the climate problem has to come from everywhere. So graphic artists are incredibly important, for example, in the communication of science. Social scientists, including psychologists to economists, in how we explain and communicate to society and take society's views into account. And local solutions, often people think, oh, I have to travel, go to a big city with a big university to make an impact. But maybe actually some of the solutions will come from local communities who know their environment, know what climate change is doing there, and will come up with very ingenious solutions that can then be exported to other communities. So I think it's really a time of opportunity and of doing things differently, for new ideas of how to work in teams, new ideas of how to connect similar communities across the globe who have similar problems and share expertise. And to me, this is really an exciting time. So I'm trying to convince my children that they should go into some environmental science, something, because it is very exciting. It's definitely not a time of stagnation, but it's a time of really thriving creativity.
Well, I love the way this closed out. I want to thank the three fabulous presenters for characterizing not only the nature of the challenges we face, but the really huge opportunities associated with the kind of transition that can sustain a vibrant biosphere and robust economies around the world. And for the note of hopefulness that even though this is a big challenge, there's a tremendous pool of human creativity out there that if we can tap into and tamp down the vested interests, work as effectively together as a global community as possible, that this problem eventually we can solve, but we don't have much time. And I think, as all of you have emphasized, the critical need is to transition from thinking of climate change as a priority to thinking about it as the priority for the coming decades. I also want to thank TNQ and Janelia for the chance to have this conversation. And with that, let me turn it over to Janine for a closeout.
Thank you, Chris. I just have a few closing words before we finish up today. On behalf of TNQ and Janelia, I would like to extend a very sincere thanks to you, Chris, for very artfully moderating this fantastic event today. Of course, I also echo your thanks to our speakers, Ram, Yadvinder, and Fiamma, for your very thoughtful and very revealing talks and discussions today. I want to also extend a sincere thanks to some key people who worked hard behind the scenes to ensure the success of today's event. In particular, Dr. Mahesh Sankaran, who provided invaluable help collating audience questions. Mahesh actually leads a group at NCBS, which is focused on community and ecosystems ecology, trying to understand how climate change impacts distribution, structure, and function of global tropical ecosystems. So Mahesh, thank you so much for your help today. I also want to thank the many technical experts who made sure everything ran smoothly for us. And these include Matt Staley, John Rapole, and Alex Fadiev at Janelia, as well as Praveen Akambran, Muralitharan Ramayakumaran, Swapnil Mida, Niyati Ramesh, and Vidita Saxena from TNQ. And very importantly, we want to thank you, the audience, for joining us today and contributing some really thoughtful questions to the overall discussion. If you would like to go back and watch this event again, and we hope you do, or if you want to share it with others, you are welcome to do that using the exact same YouTube link that you used to watch today. And there will be a recording of today's events. So again, thank you so much to everyone. And we at TNQ and Janelia hope you all have a great weekend. Take care.